Hey everyone, so today I wanted to try a new approach to communicating science research. And in particular, instead of giving the usual conference talk about a recent result, I wanted to adapt it into an animated video that's rewatchable and hopefully more intuitive and pedagogical. Ultimately, I'd hope that this format can help make research more understandable to practitioners as well as those outside the field. And so with that said, I wanted to present an animated research talk on a recent paper that I published titled Variational Neural Network Onslots for Continuum Quantum Field Theory. So let's jump on in. In unpacking the results of this work, I would first like to go over variational methods in quantum mechanics, and then introduce a new powerful variational onslots known as the neural network quantum state. Afterwards, I'll discuss our work in particular, in which we apply the variational principle to quantum field theories using these neural network quantum states and probe ground states therein. To lay the framework for this project, what we're interested in is approximating the ground state of a quantum system, that is, determining its eigenstate of lowest energy. And this is a particularly interesting problem across quantum physics because ground states can describe low temperature behavior such as quantum phase transitions in condensed matter, and they also encapsulate molecular and atomic properties in quantum chemistry. However, exactly determining a ground state is intractable in general, and so we often resort to approximation techniques like the variational principle. And if you recall from quantum mechanics, the variational principle states that the energy of a quantum system, that is, the expectation value of the Hamiltonian, is always going to be greater than or equal to the ground state energy. And one can use this principle to their advantage by constructing a variational wave function, psi sub theta, with some variational parameters, which I've noted here by theta, and then minimizing the energy with respect to these variational parameters to obtain an approximation to the ground state. In practice, what this looks like for sufficiently expressive onslots is that we minimize the energy over a handful of iterations, and what we find is that the energy asymptotes to a fixed value, which is the ground state energy. And as a result of this, the variational wave function then is a good approximation to the ground state. Now, while a variety of variational onslots exist for different applications over a wide range of problems, the recent success of machine learning has inspired the application of deep learning to this problem, and this has resulted in a new variational wave function known as the neural network quantum state. As an overview, a neural network quantum state is a wave function parametrized by neural networks, whose parameters are then optimized over to approximate the ground state. In its simplest incarnation, one could imagine decomposing a wave function into an amplitude and a phase, which are then parametrized by feed-forward neural networks. Although I will note that more intricate constructions exist, they use Boltzmann machines, recurrent neural networks, transformers, and so on. Let's now take a look at how these are used in practice, and in particular, we need a method for estimating and minimizing the energy of a neural network quantum state. For this, we can use a technique known as Variational Monte Carlo, in which we estimate the energy with Monte Carlo techniques. To see how this works, we can first express the energy of some wave function psi as the expectation value of the Hamiltonian, which we can then expand as the following integral. Now if we multiply and divide by psi, and rearrange some terms, we can re-express this quantity as follows. What's important to note here is that the first term, which I'm highlighting here in this box, is the probability distribution of the normalized wave function psi. And in addition, the second term here, h psi divided by psi, is something that we will call the local energy and denote by E loc. With these two identifications made, we can then express this quantity as an expectation value of the local energy, where this expectation value is taken over the probability distribution of the wave function psi. So overall, this has allowed us to express the energy as a classical expectation value. In practice, we can estimate this expectation value by drawing samples from psi squared using Markov chain Monte Carlo sampling, and then estimating the expectation value as an empirical mean. Moreover, because we're using variational techniques, we're also interested in minimizing the energy. And to do this, I will note that you can derive a similar expression for the gradient of the energy with respect to some parameters theta, from which we can minimize the energy using gradient descent techniques. Now, using this methodology, neural network quantum states have been applied to a wide variety of systems, like spin chains in condensed matter and molecules in quantum chemistry. In these settings, they've been shown to outperform traditional methods, such as tensor networks on a two-dimensional lattice, as I've shown here in this plot, and also outperforming the Slater-Jastrow onslots in quantum chemistry. In addition, another piece of evidence in favor of neural network quantum states is a recent paper that showed how neural networks can perform tensor network contractions with little overhead. And what this tells us is that neural network quantum states can encompass tensor networks in their expressivity, which is illustrated in the following figure, and we therefore have even more reason to believe in the strength of these neural network quantum states. So evidently, these neural network quantum states are a powerful hammer that can hit a bunch of nails. And in our new work, we aim to strike another nail. That is, we wanted to employ neural network quantum states to approximate the ground states of quantum field theories. So this is what we study in our recent paper that I alluded to earlier. And the punchline here is that we use these neural network quantum states to extend the variational principle to non-relativistic field theories and approximate ground states in that setting. So let's take a look at how we were able to do this. Our goal here is to extend the variational principle to quantum field theories. But in general, this is actually a pretty non-trivial problem, which Feynman noted in one of his later works here. The primary challenge here lies in constructing a variational ansatz for a quantum field state whose expectation values can be efficiently computed and optimized. And moreover, a current numerical tool that we do have for this problem is something known as the continuous matrix product state. And while this works in some simple cases, it does tend to struggle in inhomogeneous systems and systems with long-range interactions. So ideally, we want to build a tool that can do better than this. To take a first stab at this problem, let's consider non-relativistic quantum field theory. In this setting, the number of particles isn't fixed, and so a quantum field state is really a state in Fock space that can be represented as a superposition over n particle wave functions. And so here I'm denoting our quantum field state by capital psi, which is a superposition over n particle wave functions that are denoted by phi sub n. In practice, what this looks like is a sum over a zero particle wave function, which corresponds to a system with no particles, plus a one particle wave function that corresponds to a system with one particle, plus a two particle wave function that corresponds to a system with two particles, and so on. Moreover, in our work we study bosons, in which case each one of these n particle wave functions is permutation invariant in position space. So overall then, our goal is to construct a variational ansatz for this quantum field state, which is challenging because it requires a way to parameterize over the infinitely many n-particle wave functions, each of which takes in a different number of arguments. In particular, the zero-particle wave function is just a constant, the one-particle wave function is a function of one variable, the two-particle wave function is a function of two variables, the three-particle wave function is a function of three variables, and so on. And so then what we want is a variational ansatz that can collectively parameterize all of these n-particle wave functions in a compact expression. So let's see how we can do that. To model such a variational ansatz, we use a recently developed tool known as the deep sets neural network architecture, which was constructed to model functions of a set, say some set A sub I, and has recently been deployed in the context of neural network quantum states. Deep sets are constructed from two neural networks, which I will denote here by rho and phi, and they output the following function, which I'll denote by ds, which takes in as input some set A sub I. So the function that they output is given by the following expression. The interpretation of this function is that phi acts as a feature embedding that is applied to each element of the set, and then all these features are aggregated together in the big summation, which is then passed through rho to add correlations to these embedded features and output a function of interest. So with that said and done, I will note two key properties of deep sets that we will use in our work. First, this architecture is permutation invariant due to the presence of this sum. That is, we can rearrange the terms in this summation under any permutation, and the output will still be the same. And second, this architecture is able to accept an arbitrary number of arguments by including additional terms in the sum. And these two key properties are exactly what we need to model quantum field states. It's permutation invariant, so it can represent bosonic wave functions, and it's also able to accept an arbitrary number of arguments, so we can model all of the n-particle wave functions collectively. Using this insight, let us introduce our new ansatz, known as neural network quantum field states, as a variational ansatz for quantum field theories. So as we had on the previous slide, a quantum field state can be expressed as a superposition over all of these n-particle wave functions. And in position space, an n-particle wave function can be written as follows, where this input, boldface x sub n, is shorthand for a vector containing n entries, or n positions. In our neural network quantum field states architecture, we choose to parameterize each one of these n-particle wave functions by a common deep sets architecture. Now, I'll emphasize here that we're using a common deep sets architecture to parameterize all of the n-particle wave functions collectively, And our ability to do so stems from the fact that these deep sets architectures can take in an arbitrary number of arguments and can hence parameterize a whole collection of functions rather than just a single function. So I will note then that in this architecture, we're using a finite number of neural networks to parameterize all of these n-particle wave functions. And in addition, all this work is being done in the continuum limit, so we're using no lattice or discretization. So now that we've introduced our ansatz, we will need a method to estimate and minimize its energy. And for this, we can use variational Monte Carlo as before, but now accounting for the variable number of particles in the setting of quantum field theory. So I won't go into all the details on the math, they're contained in the paper, but in essence what we do is we can again express the energy of our quantum field state psi as follows, and using the principles of variational Monte Carlo, we can re-express this quantity as a double expectation value of a quantity known as the n-particle local energy, which is given by this expression here, where in this double expectation value, we are taking in the expectation value over the number of particles according to the particle number distribution, which I'm denoting here by p sub n. And this is given by the following expression, which in essence is just the norm of the n-particle wave function divided by the total norm of the quantum field state. And the second expectation value is taken over the positions of n particles drawn from the probability distribution of the n-particle wave function, that is, phi n squared. And so overall, this expression here is just like the expression we had for the energy using ordinary variational Monte Carlo, but now generalized to the case in which the number of particles is indeterminate, and hence we also have to take the expectation value over the number of particles. As before, we can estimate the energy using Markov chain Monte Carlo sampling, where we're now sampling with respect to the number of particles and the position of those particles. Moreover, I will also note that we can derive a similar expression for the gradient of energy with respect to some variational parameters, which we can then estimate and then feed into a gradient descent algorithm to minimize the energy. Now, as it turns out, sampling over both the number of particles and the position of those particles is actually non-trivial because each sample can contain a different number of particles and hence can be a vector of different length. As we show in our work, we can actually adapt Markov chain Monte Carlo methods to accommodate for this, which allows us to then sample with respect to both p sub n and phi sub n squared simultaneously. We achieve this by adapting the traditional Metropolis-Hastings algorithm to a setting in which the number of particles can change. This is accommodated for with a proposal step that allows the number of particles to increment or decrement by 1. Starting in a particle configuration denoted here by x sub n, we could first imagine perturbing these positions to generate a new configuration, which I denote here by x sub n prime. We can secondly imagine randomly adding a particle to generate a configuration x sub n plus 1. And third, we can imagine randomly removing a particle to generate a configuration x sub n minus 1. This ultimately allows us to sample from both p sub n and phi sub n squared simultaneously in a single MCMC chain. Before going on to the results section, I want to briefly recap what we've achieved here. We've introduced the deep sets neural network architecture and shown how we can use it to parameterize a whole collection of n-particle wave functions. This collection of parameterized n-particle wave functions then constitutes our neural network quantum field state ansatz. Using this ansatz, we can then minimize the energy of some Hamiltonian using the techniques illustrated on the previous slides, and upon optimization, this will ideally provide a good approximation to the ground state of that field theory. So that completes our description of neural network quantum field states. And with that said, let's now look into some applications. In our applications, we will look at 3 models: an inhomogeneous system with hard walls at the edges, a system with long-range interactions in which the potential decays polynomially, and lastly, a system that violates particle number conservation. Let's now take a look at our first model, which is known as the Lieb-Liniger model, and is given by the following Hamiltonian that describes bosons interacting via a point interaction of strength G. In this Hamiltonian, the first term corresponds to the kinetic energy, the second term corresponds to the chemical potential energy, and this last term here corresponds to the interaction between the particles, in which the interaction potential is given by a delta function of strength 2g. In studying this model, we will consider an inhomogeneous system with hard walls at 0 and L for some system size L. We will also consider the strongly interacting limit in which g takes a very large value. So with the following parameter values, what we find is that, first, the energy density agrees very well with the exact solution, And in addition, the particle number density also agrees very well with the exact solution over the range of the system. Next up, we'll look at a system with long-range interactions, which, as I noted at the beginning of this talk, is a regime in which prior numerical tools struggle. For this study, we will look at the Caligaro-Sutherland model, which is given by a Hamiltonian analogous to the one in the previous slide, but where now the interaction potential is given by this following expression. And this might look kind of funky, but what it really is just a 1 over r squared potential on a periodic ring, hence the presence of the sine function. In applying our neural network quantum field states to probe the ground state of this system, what we find is that again, the energy and particle number agree very well, as does something known as the one-body density matrix, which acts like a sort of correlation function for this model. Lastly, let's take a look at a model that violates particle number conservation. And for this, we will consider the following Hamiltonian, where this last term here is the term that violates particle number conservation. And studying such a system is interesting because its ground state will necessarily be a superposition over n-particle wave functions. And so we will really have to exploit the ability of neural network quantum field states to parameterize a whole collection of functions rather than just a single function. I'll also note that while this Hamiltonian might look a bit contrived, it is actually mappable to a renormalized Klein-Gordon model, and it can be derived from that. So we studied this model over a wide range of parameters, and what we found is that the energy density agreed very well with the exact solution, with increasing errors as we approach the critical point in this model. Moreover, to illustrate that we're truly learning the correct superposition over n-particle wave functions, we also looked at the probability distribution of the n-particle wave functions, that is, p sub n. And as I show here in this plot, what we find is that our ansatz agrees very well with the exact solution over a wide range of particle numbers, which emphasizes the expressive power of these neural network quantum field states. So with those applications presented, this brings us to the end of our animated research talk. To recap, here we've developed neural network quantum field states as a variational ansatz for quantum field theories and demonstrated their application to various systems, including an homogeneous system, a system with long-range interactions, and a system that violates particle number conservation. But, of course, the work on neural network quantum field states doesn't have to stop here. An enticing direction that one could take is to adapt these tools to relativistic systems, which would require some modifications to avoid issues like UV divergences that we face in relativistic field theory. In addition, while here we've only studied systems in one spatial dimension, this framework is generalizable to higher spatial dimensions by treating the particle positions as a vector of the appropriate dimension. Studying such a system in a higher dimensional space would be particularly interesting because traditional methods like continuous tensor networks and continuous matrix product states tend to struggle on systems in 2+ spatial dimensions. And more broadly, in this work we use neural networks to model functions that can take in an arbitrary number of arguments. And so some food for thought here would be to consider where else in physics or math do we need to model such functions, because now we have a tool for doing so. And for those who are interested in learning more about our work, our paper here is on the archive and in PRL. So, thanks for listening, and I hope you learned something today.